All right, welcome back, everyone. We're going to continue on with our conversations on concrete. This one is actually our part two. Last time we talked about materials, the material properties involved with concrete. This time we're going to look at the mixture proportioning, because we did say that there's water, cement, aggregate, both coarse and fine, and air. We mentioned that last time. Now we're going to talk more about the effects of changing that mixture up in proportions. And also testing the concrete to make sure it's where we need it to be. You can see this is part 2 of 6, so this is working our way through concrete, but there's a lot of concrete to go through. So let's start with properties. Now, this corresponds to section 3.7 in the book. And when we think about the mix and what factors we're going to be looking at, there's really two states to concrete. One is its plastic state, which is that, still in its, I don't want to call it liquid because there's other stuff going on there and it's a little thicker than just a liquid. But that's its wet state when you're pouring it versus a hardened state after it has cured and become a solid object. And we are primarily concerned with things like the consistency, workability, and finishability in its plastic state. What that basically means is how easy is it to spread around, get it into the voids, how easy is it to finish it with a trowel, make it look pretty afterwards, versus the hardened state after it's cured and hardened. Then we're more concerned with how strong is our concrete, how durable is it going to be, how much will it resist water penetrating into it, and will it be resistant to wear and tear. Concrete gets its strength from the cement. That's really where the strength of our concrete is going to come from. It can be affected by all the other factors as well, though. So water content, the more water, the less strength. We'll talk about that a lot in just a bit here. The cement content, more cement makes it stronger since that's where it's getting its strength from. The air content in the mix, we talked about some benefits of having air in your mix before with this freezing and thawing conditions and how it allows the concrete to be able to absorb that. But it does decrease the strength of the concrete for the air in the mix. We'll talk about that as well in a little bit. And finally, aggregate type and gradation. So once again, last time we talked a little bit about having a good sorted, gradated aggregate where we had many different particle sizes. So the key factor about concrete is it's really strong in compression, but it's not very strong at all in tension. And so what we can see here on this bottom one is like a beam. And if you think of how a beam works, when you're bending a beam or putting a load on here, what happens is the top of this beam is in compression, so it's nice and strong, but concrete is really weak in tension. Well, that's what's going on in the bottom part of our beam. It's pulling, right? So because of that, we typically need to reinforce our concrete with something, typically rebar or possibly GRFC, a glass fiber reinforced concrete. There has to be something that can handle the tension, the pulling part. That's why you don't see like concrete that is strictly under tension. It just wouldn't make sense. We're also concerned with this idea of durability. And durability, you probably know the word durable. Same thing with concrete. As it's weathered with moisture, temperature, chemicals, abrasion, we don't want the concrete to start falling apart. You can see some pictures over here where it's not doing so well as far as the durability. You can see it flaking off and peeling off the bottom of an underpass. It always makes you nervous when you drive underneath a bridge and you see this rebar down here is exposed, because like we just said, the rebar is the part that's holding the concrete together in tension, right? So if your rebar gets exposed like this, then rebar made out of metal can start to rust, and once the rebar rusts, it becomes thinner, less strong. That's when you have a collapse. So we are concerned about durability. We want to protect that rebar. And some things that can affect that durability would be the amount of water we're adding, the cement, the air, the aggregate. Basically, those are all of our elements in our mix, right? The only thing that's different here is finishing and curing, because if we didn't, say we finished it in a way that didn't have, that allowed water to collect or pool or something like that, or if we had poor curing conditions where possibly it froze before it was fully cured. We're also concerned with workability. So how easy is it to be put into the place where you want it to be? And just like before, if you look at all the ingredients, it affects workability. Water, actually, if you add more water, it helps with the workability, makes it easier to flow around and get to where you need it to be. But like we said earlier, it decreases the strength. The temperature during placement, so if it's a really hot day versus really cold day, that can affect how workable this concrete is and how fast it's setting up. The air content of the mix, more air does make it more workable, but also decreases strength. And any kind of chemical admixtures, like I think we talked about super plasticizers last time, which make it more, in essence, liquidy. It acts like you've added more water, even though you haven't added more water. So you can add these chemicals in there. That'll affect how workable it is. So let's move on to concrete mixture proportioning. What about our proportions? The most critical one we talk about is the water to cement ratio. Definitely, you'll hear this all the time. And this is a ratio of water to cement, as you could guess. And as I've already said, the more water, then the less strength. And here we can actually see a diagram where we have air entrained and non-air entrained. Let's just look at the non-air at first. And what we're saying is if we increase our water to cement ratio, so we're increasing our water, we see our strength decreasing drastically, right? Now, if we have air in there, it decreases even more. It parallels it only. It's slightly below. So what do we have here? We have some general guidelines. 3.5 gallons is needed for a 94-pound bag of Portland cement. So for the CM majors, you'll probably have an estimating class where you're estimating how much water you need to mix with your cement to create your concrete batch, and so this would be the baseline, the absolute minimum, and this gives you a water to cement ratio of 0.31. Now that is not very workable, and no one would be happy if you said we had to have a 0.31 water to cement ratio. So we're going to add a little bit more water to make it more workable, but there's that fine line. Too much water, you lose strength. Too little water, it's not workable. So to provide a workability, we're really saying from 0.31, we're going to bump that up to 0.35. That's still really low. Up to 0.5. So somewhere in that range is really what we're saying to make the concrete workable and still keeping our strength. There is a maximum water to cement ratio. Like I said, we're targeting 0.4 to 0.45. Usually this is stated somewhere because if you go too high, then you're losing your concrete strength. Speaking of strength, like I said before, there's a direct link between strength and water cement ratio. Here you can see as our water cement ratio goes up, meaning we're adding more water, our strength goes down, and we can go from 7,000 psi with this very low water cement ratio of 0.33, and it drops all the way down to like 4,000 or 3,000. So you're getting like half the strength out of your concrete if you add that extra water. So that's why it's so important, because on site it's a little harder to make sure that you have the correct amount of water to cement ratio, especially if you're either batching it on site or if you have trucks coming in and they're spraying it down because they've been sitting for a while or whatever else might be going on. So what happens if you have too much water? You can have excessive paste. We'll talk about what happens with excessive paste in a little bit. Increased porosity, so you have these voids in there. Decreased density of the gel, decreased durability. We said how important durability is, and we want to not have that happen. And susceptibility to freeze and thaw cycles. So all of this is bad news. Ideally, we want to keep that water to cement ratio in a lower, more desirable state. And when we're talking about how concrete is setting up and curing, you can see that we typically talk, I think in the last slide it actually, well, maybe not. Oh yeah, it does say here 28 days. 28 days is one of these magic numbers where after 28 days, 4 weeks, that's basically 98% of the concrete strength that you're going to get out of it. So usually that's the baseline we go on when we talk about how strong concrete's going to be. But if you look here, you can see that concrete can actually continue to strengthen for this was a whole year. I actually heard beyond a year, as long as you have it in a nice moist environment. And you can see each one of those, each one of these lines. So if you were immediately after your 28 days, you actually didn't have it in any moist, you didn't have it moist cured at all, just had it in a laboratory. You can see after you reach your 28 days, you about maxed out and you don't get any more. And of course, if you did 7 days, you're a little higher. 28 days, even more. And if you never take it out of that moist environment, then the reaction continues to happen and it becomes a stronger and stronger concrete. So we talked last time about these different types of cement, type 1, 2, 3, 4, and 5. 1 was normal, 2 was this moderate sulfate resistance if you have a little bit of sulfate in like your soil or in your water. Type 5 is you have very high sulfate, 3 is early strength, and then 4 was low heat hydration. If we compare it to normal concrete, meaning this is the strength of normal concrete is our baseline, right? After 1, 7, and 28-day tests. If I were to look at these other ones, like say high early strength, that one's kind of cool to look at. So after 1 day, we're much stronger. We're at 190% versus, so you have a 90% gain here over our normal concrete. But it starts to taper down, and after 28 days, you get a little extra strength. But really, what the concern is you can get that high early strength, so you're not waiting the full 28 days to continue. If we were to look at some of these other ones, they generally are lower because they're not as concerned with strength, but these other properties like resisting the sulfate. You can see that the more you're trying to resist, the lower your strength is going to be overall. At the very end, you get kind of close to 85-90% of what you'd get if it weren't type 2 or 5. And then low heat of hydration, you can see really starts off with a low early percentage. So this slide is a little bit interesting. I think really all it's getting at is the fact that if we have air-entrained concrete, then it will not be as strong. And therefore, if we were to look at the water to cement ratios, if we had air-entrained, we need a lower ratio, meaning less water, than if we had a non-air-entrained concrete. But really, I think the takeaway here is just that if we have air-entrained concrete, then we need less water in our mix as well. Here's a general rule of thumb for how the gallons per bag of cement will affect our strength of our concrete. And, we've talked about this on a number of slides, but we still see it here too. If we have 4 gallons per bag, we could have a 6,000, I believe this is PSI, it's got to be PSI concrete. And if it were air-entrained, it drops a little bit down to 4,800. If I increase that water, gallons per bag, I can see how the strength is decreasing, even more so for air-entrained. So if I have the exact same bag of cement, it could go from 6,000 PSI down to 1,600 PSI if I add a ton of water and I have air-entrained. So some issues with excess cement paste. Now remember what the paste is. It means it's the water in the cement. It's not looking at any of the aggregate or the air. If we just have too much of the cement paste, so it's not looking at water so much, but too much of that Portland cement and water. What we end up with is an increased cost because Portland cement is the most expensive ingredient. And also we can have issues with shrinkage. And this is just a factor of cement in general, is that when it's drying, it is shrinking. And that's why we get cracks in concrete anyways, but you'd have excessive cracks or more cracking in your concrete if you have too much of that cement paste. When we talk about our aggregate size, we want to keep our segregation of aggregate from happening. We mentioned this in the last presentation where we want this even gradation. We want small, medium, and large aggregate. We don't want just large or just small. And the issue is that you can have this separation or segregation of your aggregate, and some of this can be based on the maximum size of your aggregate. So here's some general rules of thumb, or should not be larger than 1/5 the narrowest dimension of the form, and should not be larger than 3/4 the minimum clear distance between reinforcing steel. So those are some guidelines for how big your aggregate could be. In this last one, in slabs, like a slab on grade or something, the maximum aggregate should be about 1/3 the slab's thickness. So 9-inch deep slab, I suppose you could have an aggregate up to 3 inches. That'd be kind of big, but you never know. So what we're showing here is the maximum size of aggregate and in relationship to the air content. So we talked about one ingredient within the concrete is going to be air. How is that related to aggregate? And as our aggregates increase in size, you can see that our recommended air is decreasing. And it also is a component of what your freeze thaw exposure is going to be, because like we said, if you have air inside, it actually helps for your freeze thaw conditions. You want more air to help prevent the cracking of concrete due to not being able to expand and contract if you don't have the air in there. All right, so let's look at this slide. Let's summarize what we have for these relationships with each ingredient. This is a great slide. I mean, this is like a summary of everything. If we look at our cement, what is the purpose of this cement? That's really where our strength is coming from, and it binds everything together. If we have too much cement, well, we can have this shrinkage and cracking of our concrete. Also, our durability could be effective. Other consideration, well, it's the most expensive ingredient, so, your overall cost would go up if you have too much cement. Water, well, we need it because it's going to react with the cement. That's what's causing the chemical reaction. And it helps with that workability. We said the more water, the more workable. However, if we have too much water, then we have that decreased strength and decreased durability. The fine aggregates, the smaller particles, they fill the spaces between those larger ones. And we have decreased workability, and more water is needed if we have too much of that small aggregate. And for the coarse aggregate, almost the same idea. So this takes up the bigger volume of the concrete. Also decreased workability if I have too much coarse aggregate or just too much aggregate in general. And we do have to be cautious of how much cement paste we're going to need to make sure it covers all of our aggregate if we have too much of this coarse aggregate. And as we said, we want this to be well graded. So it increases density, improves durability, decreases permeability. We also said it helps with keeping the segregation of particles from happening. Air, we said the purpose of air is it'll help reduce this freeze thaw damage when you're in those conditions where the temperature drops. And it can improve workability. However, if we have too much air or any air, the more air we add, the less strength we have of our concrete. So let's move on to testing our concrete. The number one test on site to see if our concrete batches is where we want it for our water to cement ratio is this slump test. So what the slump test is, I think the next slide will talk about the process of using a slump test. But what it's measuring is this consistency. It's how moist and workable is it. If there's too much water, we'll talk about what's happening, but basically, just like the word implies, when you have your concrete, how much is it going to slump? How much is it going to just kind of fall out of place? You can imagine if you have a whole bunch of water or a super plasticizer or something that makes it real workable, then it's going to have a very high slump. If it's a very stiff mix where there's almost no water, then it'll almost stay in the exact same shape as when you first did it. It's almost like if you've ever been to the beach and with sand, same thing with sand actually. If you have a very dry sand and you flip your bucket over and you lift it up, you're making your sand castle, it stays in place. You try with a bunch of water and the whole thing just slumps out. So this is what we're doing for the test. Here you see your slump cone. Well, you fill up that cone, you're flipping it so it's shaped like a cone. You put 1/3 of your concrete mix in there, and then you tamp it down. You take this 5/8 inch pointed rod and 25 times you tamp it down, and this is really regulated. You do exactly 25. Then you pour in another third, and then you tamp it down another 25, and you try not to go into that lower layer, so you only do 25 for that second layer. Then you do it again for the third one, bringing it to the top, and it'll overflow a little bit. So you struck it off with a trowel. You're just scraping off that top part. And then you can see in the step 5, you're going to lift straight up, because if you start to go sideways, that of course will affect it and knock it over, but you're going to go straight up. And after you go straight up, you flip your cone upside down, and usually you can put the same tamping rod right on there, and you want to measure how far the slump is, because this is the original height, and that would be the distance that it changed. So here's the relationship between slump and water cement ratio. Like I said, slump's probably the number one test to test your water cement ratio. If it's a very dry, low water to cement ratio, it's not going to slump hardly at all, like 0 to 1 inches. Very hard to work with. Stiff is still pretty hard to work with, but you'll have a slump of like a half an inch up to 2.5 inches. A medium, that's more normal, like a 2 to 5.5 inch slump versus wet. Now you're starting to get great for workability, but you're losing your strength unless there's a super plasticizer or something else that's making it with this high slump. So if it's wet, you expect a slump of 5 to 8 inches. And if it's sloppy high water cement ratio, you probably have too much water in there. That's 7 to 10 inches. Unless you have a special project you're working on where you need it to flow, right? So you might have a slump like this. Like we haven't really talked, I don't know if we do talk about this, but like shotcrete, if you're going to be pouring it into something and shooting onto a wall, of course you'd have a very high slump for something like that. So application may depend, but in general, we're shooting more for these middle, medium type of slumps. Outside of the slump, we also want to test how strong our concrete is by taking samples throughout this project. We have these molds that we're going to collect the concrete in, and we're going to fill them with 3 even layers of concrete. So this is just like with the slump test. We put a third in, we tamp it down 25 times, put a third in, tamp it down, put your final third in, tamp it down. And then we test our specimens. So then we let them cure, and then we test them after 7 and 28 days are the most common times. Sometimes it'll be a 1-day test too. And that'll determine that rate of strength gain, so we can see on the graph where we are at and how strong our concrete sample is. Here you can see the test sample being crushed in the testing machine. So for the CM majors who go on to 251, this is one of the labs that we do. We make our own concrete, test and smash it in the lab. And there's a little bit on how often we should be pulling our concrete to get it tested. We'd want to do it at least once a day, but not less than 1 test for each 150 cubic yards of concrete, or as specified. Because if you have a lot of concrete coming into your mix, you want a regular, consistent, accurate measurement as we're going through the project. There's also a test to figure out how much air is in our concrete mix, and we're using this container here. And what we're doing is we're filling that container full of concrete, and just like before, we put it in layers, we tamp it down. After we do that, we put on this airtight lid, and then there might be a little bit of air stuck between the top and this lid. So what we're doing is we're putting in water and in essence bleeding it out, right? So to get all the air out, and then after we get all the air out, we close it up tight, and this little gauge will tell you what your air content is. So that's what I have for this presentation, part two of concrete. And we'll keep trucking along with concrete. So thanks for watching, and I'll see you all in the next one. Thanks.